Hello everyone and welcome back. Today we are going to talk about angular energy transfer. And if those last two words sound familiar, it is because physics has a word for energy transfer, particularly energy transfer to or from the system, and that word is work. And if you've been with me for most of the series, then you may remember that work is the second most important definition in the course. So let's start by recapping that definition. Work, the transfer of energy to or from the system. Therefore, angular work, the transfer of rotational energy to or from the system. Technically, this second definition doesn't really exist. However, since we are about to literally define rotational equation for work, this is not an unhealthy way to think about it. All right, to start out, let's discuss work and its rotational equivalent. And whenever you go from linear to angular, or vice versa, you are going to use one of these three equations. And these should be very familiar to you by now if you've been watching my angular physics videos. Okay, let's start with this situation. I have a block tied to a string that is connected to an axis that does not move. A force is exerted on the block. That force is always perpendicular to the string. Now, if the force pushes that block, it is going to start moving in a rotational pattern. And we are going to keep the force exerted on the block. And that force will continue to be at a 90-degree angle to the string, which means that block will continue to move in a circular path. Now, for those of you who remember, the work equation is force parallel times delta x, where the force is parallel to the displacement. Now, in this case, the displacement, or actually the path length, I should say, that is traveled, is not a straight line. It curves because it's on a circular path. And if you remember, this was delta s, or arc length. Now, the thing is, if the force is always perpendicular to the string, that means it is always parallel to the path length. Another way to say it is always tangent to the circular path. So at any one point in time, the force and the displacement, if you were to take a small enough piece of the arc length, are actually always parallel to each other. Therefore, in this situation, the work equation can be written as force delta S, as long as this force is at a right angle to the radius here, because again, it is parallel to any one point tangent on the circle. Now, since we have arc length, and I have this equation right here, I'm going to do a substitution. If I substitute arc length, I get force times angular displacement times r. Now, this force may be parallel to the displacement if you take a small enough piece of it, but it is perpendicular to the radius. And if I have a force that is perpendicular to the radius, and I actually have a radius, then that is a torque. Therefore, we have work is equal to torque times angular displacement. And if I bring up our linear angular chart, then this should be no great surprise. The rotational equivalent of force is torque, and the rotational equivalent of displacement is angular displacement. So I'm going to pause for a minute and add to this chart right now. First, I'm going to officially add force to the list. Force is in newtons, and torque is in newton meters. Work is force parallel times displacement. Work is also torque times angular displacement. And notice work is work, because transfer of energy is transfer of energy, which is why earlier I said technically the second definition doesn't exist. You're either transferring energy or not. Okay, so we have a work equation that works for rotational. And if you're transferring energy rotational, there's really only one kind of energy we're talking about. If something starts at rest and then starts moving around or moving at all, it has kinetic energy. So let's split this and start talking about that. First of all, kinetic energy is 1/2 mv squared. Again, I'm going to bring back our linear to angular equations. And this time, we're going to use this one. So 1/2 m. If velocity is omega times r, then velocity squared is omega squared r squared. And something you may notice, mr squared is the base equation for a moment of inertia. So if I put these together, I have 1/2 moment of inertia times omega squared. This is the rotational kinetic energy formula. And notice there is a shortcut, because all I really did is take mass and replace it with the rotational equivalent of mass. Then we took velocity and replaced it with the rotational equivalent of velocity. And if we take a look at our linear to rotational chart, that is practically what we did for all of these. I'm going to add the kinetic formula right now. Linear, 1/2 mv squared, and the rotational or angular is 1/2 I omega squared. And there we have it. While we're here, my next video is going to be all about this, and it's going to be a very important video. For now, let's set up a quick practice problem. All right, we are actually going to do a problem that we have done before, because one, I'll just show you how there are multiple ways to complete the same problem, and two, I want to put our new information into play. All right, here is the problem we did during my rotational practice video. A 35 kilogram cylindrical satellite at rest, which is over here on the right, has 4 small thrusters attached to it as shown. It is 6 meters long and has a radius of 1.8 meters. If each thruster can produce 2.5 newtons of force, how long will it take for the satellite to reach an angular speed of 6 rotations per second? So the satellite has a cylindrical shape, and the 4 rockets are at right angles to the radius. After listing our givens, the last time we did this, we got torque and we got moment of inertia. We're going to start the same way. We're going to do something different here. The last time we got angular acceleration, we went after time, and we got 3.3 hours. So we are going to do this problem again. For starters, I'm going to keep the same givens. We have the mass of the satellite, the length of the satellite, the radius of the satellite, the force perpendicular from each thruster, the fact that there are 4 thrusters, the satellite starts at rest. The final angular velocity of the satellite is going to be 6 rotations per second, which is going to be 37.7 radians per second. Once again, we will get the torque. Torque is first perpendicular times radius. 2.5 newtons times 1.8 meters. This is the torque of a single thruster. There are 4 of them. Therefore, this is the net torque combining all 4 thrusters. We will get the moment of inertia. It is the shape of a cylinder or puck. The equation for that is 1/2 mr squared. So 1/2 35 kilograms times 1.8 meters squared. And we have a moment of inertia of 5670 kilograms meters squared. All right, here's where we're going to do something different. Since we're going to go energy this route, I'm going to make an energy bar chart. It starts at rest, so there's no initial. So we have work to kinetic rotational. And it is a straight transfer from one to the other. We just derive work as torque times angular displacement. Angular kinetic energy equals 1/2 I omega final squared. We have torque, we have moment inertia, we have final angular velocity. So we are going to solve for angular displacement. That'd be I omega final squared over 2 times the torque. 5670 kg meters squared times 37.7 radians per second over 2 times 18 newton meters gives me 2023.853 radians. So I know it's large, but this is our angular displacement. It spins around many times. Now I'm going back to our linear angular chart, and I'm going to borrow the first kinematic equation. Angular displacement is 1/2 omega I plus omega f, which this is average angular velocity, or omega average, times time. Therefore, time is 2 times angular displacement. There is no initial angular velocity, so I'm just dividing by final angular velocity. I get 2 times 223.853 radians over my final angular velocity, which is 37.7 radians per second. Radians cancels. I have 1 over seconds in the denominator, so this is going to flip, and I get 11875.5 seconds. I will divide this by 60 and get 197.9 minutes. I will divide it by 60 again and get 3.3 hours, the exact same answer. So one, since we have multiple topics under our belt now, it is not uncommon for there to be more than one path to get to your answer. Last time we used dynamics and the second kinematics equation. This time we used energy and the first kinematics equation. But for the sake of this video, this center part here is the real connection. Work is torque times angular displacement, and rotational kinetic energy is 1/2 I omega squared. At this point, our linear to rotational chart is not only up to date, it is completed. For AP Physics 1 anyway. That being said, my next video is going to concentrate on rotational kinetic energy, and it is going to be a very important video. So be sure to stay tuned for that one. Other than that, I'll end it here. Have a good day. This is Mr. M, signing off.